volumes of solids. How can we find volumes of solids? And it's much like when we looked at integration to find area. Why did we do it? Well, sure, we got some nice formulas for rectangles, trapeziums, things like that, which we can just put into a formula. But then there's these shapes that we don't know, and that's when we used integration to find these unusual shapes. Well, it's the same deal with volume. We've got some nice formulas. We can find the formula for a volume of a cylinder, or a sphere, and all that. But then you have other solids which, well, we don't. We can use integration. So this is going to be our starting point. We've got some random function here. We can create a solid. Now, all the solids we're going to be looking at are ones that have circular cross sections. And so how we can get it, if it was area, sure, I just drop these lines down and we could find area. We did area, if you remember, by using rectangles. And we said, we'll break it up into rectangles, and we have some width. And we'd like that width to be as small as 0 as possible. And then we said, we're going to add all these up. Still going to use the same idea. But to create a solid, what we do is we get that rectangle and we rotate it around the axis. And so we get ourselves a disc, or a cylinder if you like, whose height is whatever that thickness is, that delta x. So the radius would be the y value, and we've got a formula for a cylinder. So the y value would be whatever function x is. So whichever axis we're going to, we need everything in terms of that variable. So sure, the radius is y, but we need the function x. And we go, okay, well, the area of that face, that circle that we've just created, we know would be pi r squared, pi times function x squared. So therefore the actual cylinder itself, the actual disc, would be this. So we're basically saying, well, instead of looking at the thickness, we're saying all these volumes, the change in the volume as we go along. But it would be that area times that. And we'll be adding up all of these. Now, this is essentially exactly the same as we did when we looked at area. The difference is I've got this pi there because of the formula for the circle, but I can factorize the pi out. It's a constant. And I'm just left with the sum of something times delta x, which is exactly what we had for area as well. So we know, well, in area, all we did was integrate this function. Well, we can do the same here for volume. But notice it becomes the function squared because of the formula for the area of a circle is pi r squared. So again, here's a random shape. So I could get some really strange circular shape. So here we go. Let's rotate it around. And you might get one of those vases that you put flowers in or whatever. But we could work out the volume of that shape if we knew what that function is. So basically all we do is this. If we want to find what we call a volume of solid of revolution, because we're revolving the function around the axis, then it's just going to be pi times the integral. But instead of just the y, or the function, it'll be y squared. And if we were to go around the y-axis, now we're doing everything in terms of y, so it'd be pi times, again, the integral, but the radius would now be the x value if we were going the other way around. Well, this now allows us to actually prove some of these formulas that you just accepted to be true. The volume of a cone, but we could now create it. How would I get a cone? If I just get some straight line, y equals mx, goes through the origin, if I was to rotate that round, we would end up with a cone. There you go, there's a wire diagram of that rotation. You might be able to see it a bit easier there. So we have our cone. So I'm going around the x-axis, so it'll be pi times the integral of whatever the y value is, but I want that in terms of x. So it'll be m squared x squared. Okay, well, just an integration question. M squared, of course, is a constant. I can pull that out. Add 1 to the power over the power, I get a third x cubed. Conveniently, I made the x value h, height of the cone, sub that in, and we get this formula. Now, of course, that's not the formula we recognise, because normally when we find the volume of a cone, we don't have the slope of the cone in the formula. But that's all right. I can work out that, well, if that's the radius, r, the y value, then I can play around with that. I know slope is rise over run, so it will be r over h. Sub that in, and we get our familiar formula, pi r squared h over 3, or a third pi r squared h. So we can actually prove that formula we've been accepting to be true all these years. The sphere is a little bit easier. A sphere, I just have to rotate this circle. Well, actually, it's not the circle I'm going to rotate, it's going to be the semicircle I'm going to rotate. We rotate that round and we'd get a sphere. 2 pi y squared, well, look, this formula already has y squared in it. It makes making y squared the subject a little bit easier. It's just going to be r squared minus x squared. Because of the symmetry, I'm going to go twice 0 to r rather than go from minus r to r. That makes life, again, a little bit easier. Remember, r squared, that's a constant. So integrate a constant, I get r squared x. X squared goes to a third x cubed. Substitute in, and that one just comes out to be what we recognise, 4/3 pi r cubed. Alright, well let's look at some shapes we don't have formulas for. Volume of the solid generated when y equals x squared, so our parabola, and we're going to rotate it around the y-axis. Let's draw a picture of that. So here is our parabola, y equals x squared. We're going to rotate that section from 0 to 1 around the axis, and we get, well, there's a wire diagram of it, a shape called a paraboloid. That's what that shape's called. Headlights of cars are paraboloids. Let's find its volume. So it'll be pi times, this time everything's with respect to y because we're going around the y-axis. X squared, need to put that in terms of y. Well, actually it already is when we look at it. Y is x squared. So we're going to integrate y to y. Add 1 to the power over the power, substitute in, and we have our answer, pi on 2 units cubed. This shaded region, so I've shaded it in blue there, is going to be rotated around the x-axis. Yeah, your eyes can play tricks on you with this one. Is it pointing out? Is it pointing in? But basically we've sort of bored a hole out of a cylinder, so that hole is a cone, if you like. So extracted a cone out of the cylinder. Much like when we looked at area, we just go top boundary minus bottom boundary. Now we're going around the x-axis, so the top boundary is the line y equals 5. The bottom boundary is the line 5x. But you square it before you subtract it. Okay? Don't go 5 minus 5x all squared. No. 5 squared minus 5x squared. That's what we have to do. Alright, so let's integrate that. Substitute in, and we have our answer. Remember I said the reason we use integration is because we don't have neat formulas for everything. But hang on, we do have neat formulas for these shapes. What did we say it was? It was, we've got this cylinder, but we're boring out the cone. So I could have just said, oh well, pi r squared h minus the third pi r squared h, that's 2/3 pi r squared h. Sub in the radius, sub in the height, I've got the answer a lot quicker. So if you recognise the shape and you have a formula, use it. Don't waste time doing all the integration. Use the formula that you know. Okay, some HSC ones. So back in 2005 they asked this. We've actually got 2 parabolas, and the area between the two we're going to rotate around. Eventually that's what we're going to do. But the first thing they've done is said, oh look, find the point of intersection, because that is going to become quite important when we're doing this question. Okay, so when does x squared equal 12 minus 2x squared? We get plus or minus 2. I've found them. And, I suppose technically my answer is wrong because I've just said 2, 4 because I've looked at the diagram and looked at the shaded area, but really I guess I should have had minus 2, 4 as well in my answer. But that shaded region now, and they've given us a bit of a hint reminding us you're actually going to have to split this problem up into 2 parts. But it does say, or otherwise, if you think you've got this other way of doing it, by all means, go and do it that way. Find the volume of the solid. So here's our picture, just like area. If the boundaries change, then we got to change the integral. Okay, there's the shape we get. Like, what, an Easter egg maybe? Maybe it's an Easter egg. A bit sharp at the sides to be an Easter egg maybe. But there you go. We know it's going to be x squared to y because we're going around the y-axis, but the boundaries change at that level there. And that's why we found the point of intersection. Because as I work my way up, we can see, well, it's y equals x squared going to the axis, but once I get past this red line, it's now 12 minus 2x squared to the axis, so it's changed. That means I have to rewrite both of these to make x squared the subject. The first one, well, already is, x squared is y. The second one will become 6 minus a half y. And I will be adding these together. So the first one's going 0 to 4. We found the y value there was 4. Then the next one's going from 4 to 12. Okay, integrate both of those. Substitute in, and there we go. Eventually we get our answer of 24 pi. So much the same as we saw with area. If the boundaries change, then we've got to change our interval. We've got a different problem. 2022, a couple of years ago. Solid is found by rotating this particular region they've given us. We don't know what k is. Okay, so it's k plus 1 sine of kx. K is just some positive number, and we're going to go between 0 and whatever pi on 2 k is. Find the value of k if the answer for volume is pi squared. Well, let's set it up. Volume, I'm going around the x-axis, so I need to square the y. So I've got k plus 1 squared sine squared kx. We're going from 0 to pi on 2k. Alright, so that's what I'm going to integrate. Well, sine squared, got to use my double angle result. So I'll change that to a half of 1 minus cos, double the angle, 2kx. So we get pi k plus 1 squared on 2, and I've integrated both of those. The one goes to x, our cos goes to sine. Substitute in, so pi squared k plus 1 squared over 4k. But remember, they said it's equal to pi squared. So now I just have to work out what k is. Nicely, the pi squareds will cancel, and playing around with it, we end up with a quadratic. Oh, if it's a perfect square, we only get one possible value, then k is 1. Last year's question. So we have this region, and this time we're rotating around the y-axis. So hyperbola, y equals 60 on x plus 5, x equals 10, and so on. Right. Find that volume when that region is rotated about the y-axis. Now, if I remember correctly, I think this was worth 4 marks. Well, if I'm going around the y-axis, I need to make x the subject, because I'm going to end up going, what's x squared? A little bit of work involved there, but there it is. X becomes 60 on y minus 5. There's the picture. But the boundaries change as well. So from 0 to 4, I'm assuming that's 4 there if this scale's right. From 0 to 4, we're just rotating that vertical line around, and then we're rotating our hyperbola from 4 to 10. Well, it's like I say, well, that first bit, that's just going to be a cylinder, and I have a formula for a cylinder. So pi r squared h is all I did for the first bit. The second bit, going from 4 to 12, I've got to do the integration. Our x squared, our 60 on y minus 5 squared. Okay, first bit I can work out, that's 400 pi. The next bit, okay, expand it out, integrate it, substitute in, eventually, oh, that was nice, they're both 600. Oh, that makes sense though, because it was 600 log y. That becomes 600 log 3. That's the best I'm going to do. I'm going to leave it as an exact answer. I'm not going to bother going to a calculator for that. 1200 pi minus 600 pi log 3 units cubed. So 12f, finding volumes using integration.